Alright, I have made a sample example program in Unity, and then this is 5 by 5 grid word, and each cells are these numbers are 0, but soon it's gonna be initialized as 1 over 4, and then expected value will be just 0. And then the green cell represents our goal state, which is the cell with the reward value with positive 1, and then the red cell represents um, the trap cell, which has the reward value as negative 1. So let's first evaluate their expected value first. So since we didn't update the policy, so the probability, since we didn't update this state transition probability is just a 0.25, and then expected value for this cell after the first iteration is 0 because the neighboring cells expected values are just 0, so there's no update. But if we look at this cell, the next cell is has negative 1 real value, so this cell's expected value is negative 0.25. Just like that, if we look at this cell, the neighboring cell is our goal state, so it has positive 0.25. Same here, same here, same here. And in this game, I choose to update the expected value of this trap cell as well. So trap cell's expected value is 0.25 because it's right next to the goal state. And sometimes doing this is kind of interesting because when the reward value is way larger than the negative reward, say negative reward is negative 1, the bad reward is negative 1, and then our goal state's reward say is like 100. So the goal state reward is way larger than here, so there's not that many of loss if you directly go through this trap and to the goal. And that is surest path, and again, the reward of this goal state is way larger than the negative reward, so it doesn't really matter that for the agent to be able to just go through this trap. So it is a fair game. And then that was the first iteration, and then let's evaluate the policy. So what we expect to see for the policy, when I mean the policy means the expected value, I'm sorry, the state transition probability of each action should be changed accordingly. So these are all now 0.25, and let's type v, u, and now the state transition probability is changed. An interesting thing is, since that was negative reward, so state transition probability is now changed to 0 for moving down, while all the other directions are like 1 over divided by same maximum number, which was all 0.25. So I'm pretty sure these values are 1 over 3 because we have 1, 2, 3 maximum previously. And if we look at this cell, well, since all the neighboring states expected values are all 0, so there's no actual updates. So what we have here is not the initial value 0.25, but the new state transition probability as 1 over 4 for each direction. And similarly here, if we look at this cell, we have all this maximum state transition probability for moving left, so we have number 1, and for the other directions, just all zeros. So if we keep doing evaluate cell and update the probability and evaluate, update, evaluate, update, evaluate, update, then we are gonna somehow converge into some sort of state where that doesn't really update anymore. So this is the final state. So if you look at this cell, expectation value is like that. We can either move to right or down. Say if we move right, then we have only one option because that's the highest probability of moving right. And we move right, and same reason we move right and move down, move down, move down, and we now reached our goal. And since we have moved to down, um, say we move down to the down, and then we have state value like that, and then we have highest probability of moving to down, so we have really no other option. And then same thing happens, so we will reach to the goal. So well, it makes sense because well, either you go that path or that path. They are actually they have same distance, and you will reach the same goal. So well, yeah, it works. So then now let's look at the code. So this Unity script file has these six other scripts. For now, let's ignore Agent 2, and let's start the code from the environment script. So this is the environment script, and what I have here is it's just a delegate function to make a new prefab of the Unity, and because I don't inherit this mono behavior, so I cannot create a new object in the game scene. So to be able to make a new sort of figure in the Unity, I want to have these delegate functions, and that is the set grid. That's our constructor, and it's just the size of each cell, like width and height. And this is get reward function. So environment will give our main algorithm um, the real value given a state. And this is like get next state given action. So given current state, and you choose an action from the main algorithm, and I'm sorry, that's the current state, and that's the state table. And given all these three information, when your agent chooses an action, this environment will return a certain state to the main algorithm. So when action is equals to moving up, which U for up, and then your new state will be same X, and then new state will be for Y it is -1, because if you think about the matrix like S00, S0 1 and or S1 comma 0, if you move up, your index for the row is decreasing if you move up. So that's just it. And then if you are in a boundary cell, then you will return this environment will return this dummy state with the real value 0 and expected value 0. And that's it. And same logic here. And that's just a checking boundary. And I didn't go really too much detail for this code itself because I assume you understand the basic concept of the coding, and then other like for and if statements. So that was the environment, and then let's look at the state class. The state class has really nothing too much. It's just it has a dictionary, and it has action index, action label, and its probability, and that's it. And if we go to cell has really nothing but this game object to represent whether it is goal or not. And that's it. Just a draw policy draw value, and it's just updating the GUI. So this state class has cell, which is just our GUI update class instance. and then our agent is here, and this agent has this just initialization. This is just what is it? Yeah, evaluate policy function. So when we evaluate, it'll just go through this. So we have new value table, and new value table will be the new state table for the next state. So let's look at this first. We are initializing new value table n by n, like width by height. So in this case 5 by 5, because we have 5 by 5 grid word. And we initialize each state's value as 0. And then now we're going to iterate. So first we're iterating all this 5 by 5 grid. So for each statement we'll iterate these 25 states in the grid. And then for each state we want to look at each action, each possible action. So we have 4 actions for each state. So we're going to calculate this. And this is same process as if I write this as just this. So this part is sigma, what is it? Sigma of pi, state and action, times value of next state, given state s and action a. It's just this, calculation of this. And then as we can see here, we are getting the next state first to get the next state's reward. And oh, I wrote this incorrectly. What's our equation here? So that's our reward, yes. So we had this equation, and times reward t plus 1 times gamma and value of s t plus 1 given current state and action. So it is calculation of this equation. So we're going to get the first next state first, because next state object has the reward and next value, that and that. So that's it. That's just environment that get reward, and you put next state and then just calculate. It's just nothing but this equation. I don't know how to explain this more. That's it. You just iterate 4 times because we have 4 different actions. And then that's the new value, and then new value, I just round it. And then I put that into the new value table. For so far we have been seeing this policy iteration. Policy evaluation, and let's look at policy update part. So it's the same. So if it is goal, just do nothing. And then, oh, by the way, at the very beginning of the function, obviously we're going to iterate these 25 states, and then for each state we want to initialize this new probability with all zeros. And then we're going to create max list index, which is maximum Q functions list. And then we're going to choose some of them and then calculate correspondingly. Let's look at this. So for each state, we have 4 possible actions. So we have for loop for each action of the state. And do the same thing. We just calculate the expected value of the direction of the action. And then if that action temporary expected value is same as value, the previous value, then we're gonna add it because we have like duplicate maximum numbers. But if it is not duplicate, then we're gonna have update the maximum index list, which is clear it and then add. Then we have only one maximum number. That's it. And then we just divide 1 by the maximum list that count because that's our new probability. And then if the maximum list that contains I, which is the index, then our result probability will be this, the probability here. And that's it. And other result will be all zeros. So, and then we assign this new state transition probability for each direction. And this is just a GUI update. Then eventually, again, let's look at this. Oh, I didn't explain this. So we have this main player with the thread, the main thread of the Unity, and if we press R, the GUI will be reset. Not only GUI, but all the state will be reset. And then if we push E, the keyboard E, is going to evaluate the policy. And if we push U, it's going to update the policy. And V and A is for the other algorithm that we are going to talk soon. So for now, ignore this two. So E for evaluating the policy and U for updating the policy. And that's our main algorithm, main thread of the Unity. And when the E is pressed, this function will be called the evaluation. And then if U is pressed, this function will be called.